Thank you all. We will move to our second presentation today. This one is on layered bismuth manganese trioxide heterostructure solar cell applications. The presentation is by Dr. Wajood Diery, and I will turn the floor over to you immediately.
Good morning, everybody, and welcome to my presentation. My name is Wajood Diery. I'm working with Professor Alexei Kolpak in Kolpak Group in Mechanical Engineering Department. Today I'm going to present the research we are working on, which is titled Layered MnO3 Oxide Heterostructure for Solar Cell Applications. Solar energy is considered one of the most abundant clean energy, and it shows great promises in countries or areas with enough sunlight, such as Saudi Arabia and Gulf area. A solar cell or photovoltaic cell, which is a device that converts energy from sunlight into electricity. There's three basic steps for this process. The first step is the absorption of the light that will generate whole electron pair. The second step is the separation of these charge carriers to avoid recombination. Third process, which called the extraction into external circuits. Silicon-based materials are the leading technology for solar cell applications, although there is an ongoing effort everywhere in the world to find new materials with equivalent or improved efficiency for solar cell applications. Recently, oxide heterostructures have been proposed for solar cell applications. So in present work, we are exploring this model of heterostructure solar cell applications, namely on bismuth manganese oxide thin films. So why did we choose this material specially? First, it has band gap of 1.2 electron volt, which is in the ideal range of harvesting the sunlight reaching the Earth surface, which is about where the 93% of the solar radiation in the visible and infrared regions of energy between 0.31 electron volt to 3.1 electron volt. The second reason is that the thin film, PMO's thin film, is polar interface. The bismuth atom and Mn are both have 3+ valence, while the oxygen is -2. So that makes the MnO2 layer negatively charged, where the BiO layer positively charged. This will induce an internal electric field between these layers. This electric field will drive or help to drive the charge carrier generated from the energy that absorbed into to help separate the charge carrier and help to drive them for extraction. The third reason to pick up this material that it's multiferric, which means that it's ferroelectric, that it has a spontaneous electric polarization which can be reversed by applying electric field. And these properties come from the presence of the bismuth atom in the oxide. And at the same time, it's ferromagnetic, which means that in the presence of the magnetic field, the Mn atoms, the electrons in Mn atoms will align themselves in a parallel direction. So these properties makes the BMO thin films an interesting material to be studied for further application rather than the solar cell applications. So we use the density functional theory, DFT, which is a quantum molecular modeling method used to investigate the electronic structure of the ground state of many body systems. We will use the DFT to calculate the density of states, which gives the states that are available in the system to be occupied, and we will calculate the projected density of partial or projected density of state, which gives the contribution of the atomic orbitals in the total density of states, and we will calculate or plot the energy band structure of the system, band structure that gives the interval of energies, which is called band, where the electrons are allowed to be there, and the range or band of the energy where the electrons are not allowed to be there, which is called band gap. Density functional theory, DFT, is supported by many softwares where we're using quantum espresso package and using generalized gradient approximation for these calculations. In all the calculation, spin, polarization, and magnetic ordering are included. So we started from the bulk BMO, which is very important to be optimized before running the calculation on thin films. It's like the building block for the thin films. So it has to be optimized first. We started from the ideal perovskite structure, which has a cubic symmetry, as you can see here. We started from the previous calculation for the lattice constant and relaxed the structure until the forces of each atom is 0. And we calculated the new lattice parameter, which is in good agreement with the previous calculation. Also, we calculated the total magnetization of this structure, which is found to be 3.94, which is also in good agreement with the previous calculations. Next, we plotted the density of states for the cubic structure. As you can see, this is for spin up polarization or electrons, and this is for spin down. These two have different density of states, which means that this structure is ferromagnetic, confirmed that this structure is ferromagnetic as we calculated the magnetization. Then we plotted the projected density of state. The black one is the total density of states, and the colored one, they give the contribution of each atoms to the total density of states. As you can see here, for spin up and spin down, there is no gap. This is the Fermi level. There is no gap in both polarization. We can adopt this material with p-type or n-type and see if we can open a little bit of gap for other applications. So the cubic is ideal structure, is not the real structure. At room temperature, the BMO has a highly distorted structure, namely monoclinic structure. The unit cell contains 40 atoms per unit cell. The early experimental structural determination of BMO suggested that the monoclinic has non-centrosymmetric C2, which can be seen here. Later, or more recently, a new experimental structural determination of BMO have been run and proposed that the centrosymmetric C2C space group is proposed for BMO. So, what's the difference between these two structures? First, for the non-centrosymmetric C2, one of its symmetry operation is 180-degree rotation around the y-axis. So for every bismuth atom with x, y, and z coordinates, you will find another atom with minus x, y, minus z. And this will cancel all the polarization, as I mentioned earlier, that the polarization or ferroelectric comes from the bismuth atoms. So this will cancel all the polarization in all the direction except the one in the y direction. So this makes this structure with this symmetry polarized structure. While the centrosymmetric C2C, which has been recently proposed, has no polarization. Due to that one of the symmetry operation of this structure is it has inversion, which means that for every bismuth atom with x, y, and z coordinates, you will find another atom with minus x, minus y, minus z. And this will cancel the polarization in all the direction. And recently, a new DFT calculations have run on both structure, and they found that the centrosymmetric C2 structure is more stable than this one. It has lower energy. However, up to date, the BMO is considered to be electrically polarized. So what causes this this undetermined in the structure is due to the preparation of the bulk samples. It requires high temperature and high pressure to be prepared, and it's hard to find pure good quality bulk monoclinic. So we started from the experimental value for both structure. We've run the calculation. We calculated the total magnetization, which is found to be 4 for both structure. They have the same magnetic, which is very in good agreement with the experimental. This is the experimental value that has been calculated. Then we plotted the band structure for both structure or both symmetries for this pen-DOM. As you can see here, this is the band structure. This is the valence band, and this is the conduction band, and this shows the band gap. It has a very wide band gap, and it's hard for the electrons in the valence band to be excited to the conduction band. Then we plotted the projected density of state for both structures. It shows the gap, and it shows this is the total, and again this is the projection, the contribution of every atom into the total density of states. Then we move to the spin-up polarization. As you can see here, there is a smaller gap, but it's not the correct right band gap. And this is normal because DFT it's very well known that it underestimates the band gap, especially in metal transition oxides. So how we can solve this problem? To solve this problem, we have to use DFT plus U calculation, our methods. So where you have a term which is called the Hubbard-U term to be added to the Hamiltonian that give the repulsion interactions between Coulomb repulsion between the electrons. So how we can decide which atoms that we have this term for? We have to plot the projected density of states and look at the most dominant atoms contributes to the total density of states. As you can see here, it's the Mn manganese atom. So we next run the DFT plus U calculations. We run for different suggested values for U, for the manganese atom, until we find the suitable value of about 8 electron volt. We added this value to the Hamiltonian. We've done the calculation and we plotted the energy band structure. And as you can see, the band, it opens up to 0.45 electron volt, which is in a good agreement with the previous calculations of about 0.5 electron volt. So now, oh, sorry. Is previous or, oh, sorry. sorry. Now what I'm doing, I'm relaxing this structure with the U value that we found to open the gap, just to make sure that we will get the ground state. Then once it's all done, we will calculate the polarization of what structure, and from there we can decide which structure or symmetry that we will use to move in for the thin film calculations. Sorry, this is the projected density of states with the U value, DFTU. So what we're going to do next. The next step is to run the calculation for the thin film. We will study structure of BMO films composed of different number of layers epithelially grown on the SRTiO3 substrate. We will compute the free energy of heterostructure as a function of the interface layer stacking and the termination of the surface to find the most stable structure. Then we will calculate the potential gradient, which will, as I mentioned before, help in the separation of the electron holes. And we are expecting to find two-dimensional electron or hole gas due to the discontinuity in the polarity. Here, the substrate, it has no polarization, while the thin film BMO is polarized. So we will investigate this probability. And finally, the efficiency in the high energy region of solar spectrum can be improved by introducing another transition metal oxide with a larger band gap, such that the layers or material that facing the sun has a larger band gap than the material underneath. We will explore this idea by introducing the BiFeO3 oxide to the structure, which has a band gap of 2.4 electron volts. The computation in this work has been performed using the facilities of supercomputers at NERSC and XT. And finally, it's indeed a great opportunity for any individual like me to conduct research at MIT. So I would like to thank Aramco company for giving me this opportunity through Ibn Khaldun Fellowship. Also, I would like to thank the Center for Clean Water and Clean Energy, especially Kate and Teresa. I truly value all the efforts that you have done for us. And last but not least, I would like to thank my advisor, Professor Alexi. She's not here yet. Okay, she said she's going to be here. And her group, her guidance and support have brought me to a new place in my professional life. She is such a wonderful person, and her group has a very wonderful group. Thank you all for attending. Thank you.